Hi, welcome to another session of Circuits and Networks. In today's transient analysis class, that is 13, we are going to see different problems and solutions pertaining to transient analysis for an RLC circuit. Here we have mentioned problems and solutions, but we are taking the same problem and we are going for multiple solutions. We are going to see the different values of inductor and the different values of capacitor and how the system behavior is going to change based upon inductor and capacitor as overdamped, critically damped and underdamped. So let us begin with the problem. Here you can see the switch in the network of figure 1 is opened at t equal to 0. Determine the transient current for t greater than 0 if the inductor value is 0.5 Henry and capacitor value is 1 Farad. If inductor value is 1 Henry and capacitor value is 1 Farad and inductor value is 5 Henry and the capacitor value is 1 Farad. The resistance, it is in series with inductor and capacitor. So the value of resistance we are going to see as the same in these three conditions. Let us start with the problem. At t equal to 0 minus means what? The switch is closed, and when the switch is closed and the circuit is run under 4 volts of supply for long duration of time, then inductor in steady state will act as short circuit and capacitor will act as open circuit. This we can see from figure 1a. The switch was closed for long duration of time. Okay, so 4 volts is supplying inductor and capacitor. And the behavior of the inductor for steady state condition will be short circuit and capacitor will be open circuit. So this is what we have gained from the given data. Okay, now with this data we have to find out the transient current solution for varying values of inductor and capacitors. So when the switch was closed for long duration of time, certain current would have flown in the circuit. Let us treat that current as I, and that current will be equivalent to, since it's an open circuit over here, 2 and 2 ohms are in series with 4 volts and the value of current will be 1 ampere. Is this clear? And if at all I want to know the value of open circuit voltage across 2 ohms, it will be equal to 2 volts. In fact, whatever the developed voltage value of capacitor voltage it is going to occur over here, it will be 2 volts only. So this you need to keep in your mind, and let us take this equation as 1. Now what are the basics which we should know from our previous classes? For a RLC circuit under different system behavior, when the switch is closed, this is what the circuit is going to give you equation 2 by applying KVL, and we have framed the second order differential equation. With this we have formed an auxiliary equation. Then we have found out the roots as S1 and S2, where alpha is nothing but R by 2L and omega naught is equal to 1 by under root LC. And the solution in general will be given as K1 e to the power of S1t plus K2 e to the power of S2t. So this we have already seen from our transient analysis class 11. You can check into that video. Now apart from this, what we have also concluded from transient analysis of RLC circuit as 3 different cases of overdamped response when alpha is greater than omega naught. The solution is given by I of t is equal to K1 e to the power of S1t plus K2 e to the power of S2t. For t greater than 0 means what? The switch is closed, and after that we have done the estimation. Case 2, when alpha is equal to omega naught, the system gives critically damped response. So the solution is given by I is equal to e to the power of minus alpha t K1 plus K2t for t greater than 0. And case 3, when alpha value is less than omega naught, The system gives underdamped response, and the general solution of transient current is given by I of t is equal to e to the power of minus alpha t k1 e to the power of j omega dt plus k2 e to the power of minus j omega dt. This further can be elaborated as e to the power of minus alpha t of k1 plus k2 cos omega d t plus j k1 minus k2 sin omega d t for t greater than 0. Further, it can be changed to e to the power of minus alpha t b1 cos omega d t plus b2 sin omega d t for t greater than 0, where b1 is equal to k1 plus k2, b2 is equal to k1 minus k2. Let us see how we are going to employ these basic formulas in the given problem. So first case, we know that the resistance value is 2 ohms, inductor value is 0.5 Henry, capacitor value is 1 farad. So let us estimate the value of alpha. Alpha is equal to R by 2L, which is equal to 2 divided by 2 times of L, which gives the value of alpha as 2. Alpha value is 2. Let us get the value of omega naught. Omega naught is equal to 1 by under root LC. Substitute the value of L and C. L is 0.5, C value is 1, and omega naught value is equal to 1.414. Now clearly here, alpha is greater than omega naught. For this, the general solution is given by I of t is equal to k1 e to the power of s1t plus k2 e to the power of s2t. Let us find out the values of s1 and s2, where s1 is given by minus alpha minus under root alpha square minus omega naught square, and alpha and s2 is equal to minus alpha plus under root of alpha square minus omega naught square. And what are the values of alpha and omega naught we got over here? Just substitute the values wherever you have alpha and omega naught. So in case of s1, it is minus 2 minus under root of 2 square minus 1.414 square. Under s2 it is minus 2 plus under root of 2 square minus 4.41 square. So s1 value will be minus 2 minus root 2. S2 value will be minus 2 plus root 2. In fact, S1 is minus 3.414. S2 is minus 0.586. Now just I am going to substitute the value of S1, S2 in this equation, where I of t is equal to k1 e to the power of minus 3.414t plus k2 e to the power of minus 0.586t. So this is the general solution when the resistor value is 2 ohms, inductor value is 0.5 Henry, and capacitor value is 1 farad. Now we need to determine the values of K1 and K2, and that can be obtained from initial conditions. So at t equal to 0, that is 0 minus, the current which is flowing in the inductor and capacitor, that is 0. Hence I am going to substitute the value of I of t is equal to I of 0, which is 0, and that is equal to k1 e to the power of minus 3.414, t value is 0, plus k2 e to the power of minus 0.586 times 0. This e to the power of values, and at 0 it will give you the value as 1. So naturally we are going to left over with 0 equal to k1 plus k2, and this will treat as equation 6. I hope you understood this step from our initial conditions. And we should also keep in our mind that when the switch was closed, the inductor was short circuit, the capacitor was open circuit. As soon as the switching position is removed from closed to open, the same conditions will pertain. In fact, there is no current in inductor and capacitor. In fact, we don't have any current based upon this inductor and capacitor which is flowing in 2 ohms. So just after switching, that is applying KVL to this loop, that is this loop, where the current is going to flow in this fashion, that current that we should understand that it is depending upon inductor and capacitor. Anyhow, this current which is flowing over here is depending upon the inductor and capacitor conditions. And I'm going to apply KVL to this loop. I'm going to get VR of 0 plus VL of 0 plus VC of 0 is equal to 0. The current through resistor due to this passive elements is 0. The inductor voltage plus the capacitor voltage. Just now we got the capacitor voltage which is open circuit voltage which is equal to 2 volts, and that is equivalent to 0. Hence we can say that the capacitor voltage is developed across capacitor, it is equivalent to the inductor voltage. Hence inductor voltage is equal to minus 2 volts. This we need to keep in our mind. Also remember that voltage across inductor is given by L di by dt. So I am going to take di by dt equal to VL by L. Therefore di by dt of 0 plus will be equivalent to VL of 0 plus by L. Just now we got the value of VL of 0 plus, whose value is minus 2, because VL of 0 plus plus 2 equal to 0 and VL value we got as minus 2. So that is why this is minus 2 and the inductor value is 0.5. Please remember this formula. This is very important. Voltage developed across inductor. And hence we can determine the value of di by dt of 0 plus is equal to minus 4 amperes per second. Let us please treat this equation as 7. Please make note of these equations which are very important in order to get the solution of overdamped, critical damped and underdamped conditions. Okay, so what we have learned? We have learned that I of t is equal to k1 e to the power of minus 3.414t plus k2 e to the power of minus 0.586t. This we have treated as equation 5. Also, from equation 6 we got that k1 is equal to minus k2, and from equation 7 we got that di of dt of 0 plus is equal to minus 4 ampere per second. With these values, let us determine the transient current for overdamped condition. So I'm going to differentiate equation 5 one time with respect to t. What I'm going to get? I'm going to get di by dt of t is equal to minus, see here you have in equation 5 k1 e to the power of minus 3.4143. Differentiation of e to the power of minus 3.414t, which will equal to e to the power of minus 3.414t multiplied with minus 3.414. Similarly, differentiation of e to the power of minus 0.586t will be equivalent to e to the power of minus 0.586t multiplied with minus 0.586. So this is how we have framed this equation 8 from equation 5. Is this clear? Right. Now di by dt of 0, which is equivalent to, just wherever we have t, there we are going to substitute the value as 0. So t is 0 here, t is 0 here, and the equation remains as it is. But we know that di by dt of I of 0 plus, which is equivalent to minus 4 ampere per second, we have to make use of that equation. So I'm going to take the equation 7 in equation 9. Just I have replaced minus 4 wherever I have di by dt of I of 0, which is equal to minus 3.414 k1 minus 0.586 k2, and also from equation 6 I know that k1 is equal to minus k2. I'll make use of this equation also, and with this k1 substituted as minus k2, I'm going to get the value of k1 which is equal to 1.414. If this is the value of k1, naturally the value of k2 will be minus 1.414, and hence I'm substituting the value of k1 and k2 in equation 5. Then I'm going to get I of t is equal to 1.414 e to the power of minus 3.414t minus 1.414 e to the power of minus 0.586t. So this is the solution for overdamped condition. I hope you understood how we have obtained the solution for transient current when alpha is greater than omega naught. Let's go with the case B, that is R is 2 ohms as it is, inductor value is 1 Henry, capacitor value is 1 Farad. So we are going to sort out this problem in the same way. Let us calculate the value of alpha. Alpha is equal to R by 2L. So 2 by 2 will give you the value as 1. So alpha value is 1. And omega naught is equal to 1 by under root LC, whose value is 1. So here clearly alpha is equal to omega naught. Hence the solution is critically damped. And the current equation for critically damped is given by e to the power of minus alpha t times k1 plus k2t for t greater than 0. I'm going to substitute the values of alpha here, that is 1, and I'm going to frame equation 11. Now equation 11 is the general solution for critically damped response. Now we need to find out the value of k1 and k2. At t equal to 0, I of 0 is 0, that is understood, and hence I'm going to substitute the value of I of 0 as 0, which is equal to e to the power of 0. This is 3 here, so that's why it is 0. So k1 plus k2 of 0. With this, I'm going to get the value of k1 as 0. Let us frame this equation as 12. And the differentiation of equation 11. In fact, we know that the di by dt of I of 0, which is equal to BL of 0 by L. So B of L, we got the value as minus 2, by L value is 1. So his value is minus 2 amperes per second. So this we are going to treat as equation 13. And then in order to determine the value of K2, we are going to make use of this equation 13. So I'm going to differentiate equation 11 once with respect to t. Then I'm going to get d by dt of I of t is equal to k1 plus k2 t e to the power of minus t of minus 1. So you have UV rule. So plus e to the power of minus t k2. And this I'm treating as equation 14. And I'm going to substitute the initial condition. That is equation 13, which is giving the value as minus 2 amperes, and we have equation 14, and we are going to substitute the value of t as 0. So I'm going to get the value of di by dt of 0 is equal to minus 2, which is equal to, you can see here, e to the power of minus 0 multiplied with k1, so k1 remains as it is. Okay, and you have e to the power of minus 0 k2, so k2 it is here. So whatever the value it is here, the k1 value is 0, that's why this term goes off. This particular term will go off because k1 is 0, and I'm going to left out with minus 2 equivalent to k1 plus k2. K is already 0, so you have k2 which is equivalent to minus 2. I hope you understood how we got this value. So k2 is minus 2. This is clear. Once we obtain the value of k1 and k2, we are going to substitute equation 12, that is k1 value, equation 15, that is k2 value, in equation 11, that is I is equal to e to the power of minus t, k1 plus k2 e to the power k2 times t. So this will give you the value as minus 2 t e to the power of minus t for t greater than 0. Now this is the general solution of transient current for critically damped condition. Let us go with the final approach where resistance value is 2 ohms, inductor value is increased to 5 Henry, capacitance remains 1 Farad. So likewise we are going to calculate alpha, which is 0.2. We are going to get omega naught, which is equal to 0.477. Now clearly here alpha is greater than omega naught. Alpha is greater than omega naught, and this general solution of I of t is equal to e to the power of minus alpha t b1 cos omega dt plus b2 sin omega dt for t greater than 0. This we treat as equation 16, and omega d we are going to estimate, which is equal to under root of omega naught square minus alpha square. So just substitute the value of omega naught and alpha. We are going to get the omega d value as 0.4. Let us treat this equation as 17, and roots of the equation will be obtained as minus alpha plus or minus j omega d, which is equal to minus 0.2 plus or minus 0.4 j. Let us treat this values of roots of S1 S2 as equation 18. Now just substitute the value of S1 S2 in equation 16. I'm going to get e to the power of minus zero point 0.2 t b1 cos of omega d, which is 0.4 t, plus b2 sine of 0.4 t. Applying the initial conditions, I of 0 plus is equal to 0, we know that. So b1 actually in this equation 19 will give you the value as 0. And from the basic differentiation of current for voltage across inductor is given by VL by L, which is minus 2 by 5, because inductor value here it is 5. So this gives you the value as minus zero point 0.4 amperes per second. This we are going to do as equation 22. And differentiating equation 19 with respect to t and substituting the value of t is equal to 0, we are going to get the value of b2 is equal to minus 1. Please check whether all of you got the value of b2 as minus 1 or not. Once we obtain the value of b1, b2, I'm going to substitute this equation 20, equation 23 in equation 16. Then I'm going to get the value of I of t is equal to e to the power of minus zero point 0.2 t sine of 0.4 t. So this is the general solution for underdamped condition. So I hope you understood how we have obtained the solutions of transient current for overdamped, critically damped and underdamped conditions. I hope you like this video. Please share among your friends, subscribe to my channel, and please press the bell icon for the future notifications. Thank you.